Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video, we'll work on a real world example where we can use the partial least squares method to do some predictions. And we are going to working on chemometrics. So we'll try to predict the amylose content in rice. And the data would be near infrared spectroscopy data that we'll use, and so this is going to be a long video, so it's divided into three parts. First, we'll read the data and visualize it and try to interpret what it means, and then next we'll write some helper functions to do some pre-processing and also do the model fitting. And in the third part, we'll then fit the models and do some changes in pre-processing and see if that affects the output or how it affects the output. So let's get into it. And here is the data source. Many thanks to the authors for sharing this data as open source. I've listed them here, and here is the link for downloading the data. I'll put that in the description as well. And here is the complete citation for the paper. So the paper is dataset for of near infrared spectroscopy measurement for amylose determination using PLS algorithms, and it is hosted on the data in brief on Elsevier's Science Direct website. So many thanks to them for hosting this data and making it open source. So story of amylose. So amylose is, of course, it's found in rice, and the chemical structure looks like this, as shown in blue, and it is about 20 to 30% of starch. And within rice itself, about depending on the variety of rice that you're looking at, the amylose content can vary from 5% to up to 24% or more. And so the objective here was to find the amylose content for different varieties of rice. So I think they've studied around 100 different varieties of rice for which they have the spectroscopy data. So how does the spectroscopy work? Here is a very simple kind of diagram to show how the data may have been collected. So you have this spectrometer that sends the near infrared light on the shines the light on the specimen, and then it reads simultaneously. It reads the uh, light that returns, and then based on that signal, it is processed to give us this spectra, and that's the near infrared spectra. That's so that's a very simple intuition of how the data is collected. Now, the spectra itself could look something like this, and this is the spectra from the data that we are going to look at. So on the x-axis, we have the wave number, so that's the near infrared region. So that's the region between our visible spectra and the infrared, far infrared. So it's in between those. And on the y-axis, we have absorbance. So the way, so this is a typo, I double type that. So the idea here is that if you when you shine the light on the rice grain, some of it will get absorbed, and based on when it gets absorbed in the rice grain, uh, this particular plot shows what bonds of what chemical bonds within the rice grain absorbed that wavelength of light. So here, as you can see, these peaks may correspond to a specific bond, such as carbon bond, carbon hydrogen bond, etc. And that can be referenced to a standard table, and that can tell us what these are, and that helps explain uh, the content of the rice grain. and what percent of a particular molecule is present in that particular grain of rice, or those sample of grains of rice, and that in turn helps calculate the percentage of amylose in that particular sample of rice for that particular variety. So this experiment was repeated several times, and so we have, I think we have more than one sample collected for uh, each variety of rice to find the amylose content. I hope that gives you at least some idea as to how the data was collected. And when you download the file, there are two files you'll need. One is the mmc3.mat file, mat for MATLAB. If you have MATLAB, you definitely can go ahead and check out what these files have, and they have developed this cool software. I haven't looked into it, but based on what they have described in the paper, it has several in-depth methodologies to analyze the data. We won't be going into that much detail, but that's something you could check out if you are interested. And the mmc2.xls, that's optional file. You could download as the Excel file that has the readings from the iodine standard, and another, there's two columns and there's another column thing. Let's look at this. So there is a NIR model, and they compare these two for the amylose content. That's what I'm thinking. And then yep, that's it. And the paper is also available at the link that I'll post that in the description of this video. And now for data, we can look at this file. As you can see, it goes, the amylose content goes up to 30%. It ranges from 1 to 30. If this is the amylose content that they are referring to. And the second file, we'll look at it when we read it in Jupyter Notebook. So let's get into Jupyter Notebook now and see how we can do that. So here I've imported these libraries. We have this additional library, scipy.io, that we would be using, and then others are standard libraries, and I'm importing just PLS regression. You could try the PLS canonical and CCA as well, and see how that works with this data set. So for now, we'll proceed with just PLS regression. The first part is, so let's start here with the part 1. And for part 1, we are going to read the data and visualize it. So for the data, so let's call this data. And here, the first item we'll do is read file. And for reading the file, we have to read two files. One is Excel file and the other one is .mat file. So for that, we do have provisions in Python. So let's first set the path, and this is again on my desktop, and I've created a separate folder, Amylose, to save those files. So desktop Amylose, and so that's the path. And now for the file, the first I will save it in mmc3 scipy.io.load mat path plus mmc3.mat, and I'll print that. The print type mmc3. Okay, and so that's a dictionary. And if we look at mmc3 now, we see that it has the keys here. So this is the key, and that's the data we have. So when we want to extract the data, we will have to look at the keys, how many keys there are, and what is there in each of those keys. Sorry, we don't need the parentheses there. And as you can okay, keys, and so we do need the parentheses. And here we have the header, version, globals. Those probably not needed. We will need the remaining columns, the xcal, xtest on all of those. And before we work on those, let's go ahead and import the other Excel file. So iodine is equal to pd.read underscore Excel, and this is path plus and the file name is mmc2.xlsx. And now we can look at, so this should be in a data frame format, so we should be able to look at the records in that file. So we do get the two columns that we saw earlier, iodine and NIR dash model. So with this, now we can get started with looking at what's in the other file. So let's create another heading, check. And here we'll read the dictionary and based on the keys that we have and put them in arrays. So the first one, let's get the keys out. mmc3 dot keys, and okay, yeah, let me run this because I had to restart the computer. Okay, so here I have the dictionaries with header version. So let's see what all those mean. mmc3 dot um, underscore header underscore, and then that, or we can put them in square brackets. So we don't need that information, so we can ignore it. Then look at the version. It's, yeah, we don't need that either. Then look at globals, nothing in there. And next look at xcal uh, without the underscores there. Let's remove those. Okay, so this is what we need, and then we have similarly x test, so that's an array. We have ycal, that's also needed, it's an array. Y test, that's an array. And then finally x-axis, we do need that, and spectra total. So we need all those arrays in there. Now generally when the data is there, you'll have a metadata file that describes each of the columns or arrays, what they mean by the name, such as xcal means this, xtest means this. However, for this data set, I could not find that metadata in the description. Probably it's there somewhere in the MATLAB files that I didn't open. So based on the guesses, what I'm thinking is the xcal and ycal, those are for training. Then xtest and ytest, that is for the testing the model. X-axis is just an additional column for plotting purposes, and then spectra total is looks like that's the combined data from xcal and xtest. Although the total number of records do not add up, but still that has the highest number of records. So assume we'll ignore this file and we'll just use these files that are in there, those arrays. So the first one is xcal. So let's create that. So let's pull that here. Okay, so I'm going to get mmc3 and xcal dot shape, and we can look at the shapes of this now, or we look at them later. So we'll first pull the files and then look at the shapes. So that's the xcal mmc3. Then the next one is xtest is equal to mmc3 xtest. The next one is ycal is equal to mmc3, and this as the ycal. Then we have ytest is equal to mmc3, and this as the ytest. And followed by this we have x-axis. Now the x-axis, let's first uh, copy this here, and later on I'll show the why it needs to be flipped. X axis, and so for now I'll comment this line out. X-axis is equal to np.flip, and this is x-axis. And there's a reason why we need to reverse this, is because while plotting the x-axis, if you look in the paper, it starts from 12,000 on left and goes to 4,000 on right. So that's the way we need to plot. And for spectra total, I'll have this in this variable, but we may not use it. MC3, and this is spectra total. So with this, we have all the arrays in there. Okay, so we can print their sizes. So print xcal dot shape, and have xcal dot shape. Now I know that for getting the shapes, we have considerable typing to do, but the idea is that once we have these shapes, if we need to refer back, we can easily do that. Then we have x test right here, then we have y test, and that's there. Then we have x-axis, which is that, and then we have spectra total, and that's the last one. We don't need this. Again, when we run this, so as we can see, we have 203 records for the xcal, and for xtest we have 110 records, and the x-axis is 1154. So 1154 would be the number of features we have, and then 203 are the number of samples we have. So each spectra is arranged in a row, and we'll have clear idea of that as we plot the spectra. So we now have all the arrays in place. The next item we can do is visualize, and the reason why we don't need to visualize is not only to see the spectra, but also to see the correlation part of it. So let's look at the correlation, and you'll be amazed to see how correlated this data is, how correlated the features within the xcal are. So sns dot heatmap dot heatmap, and then np dot corrcoef xcal row var is equal to false, and where that to get the coefficient of determination, and then plot this. SNS is not there, so we need to add that here. Import cborn as SNS, and we can go back down here and rerun this. And as you can see, there's so much correlated variables here, features we have. So the lighter color is, so this is almost 1. So these are like 100% correlated, all these right here, and substantial number of them are correlated along there. So if we run a linear regression on this, we'll get a very, very high MAC, and we'll check that as well as we go through this exercise. The next item we'll visualize is the amylose content. And the reason why I wanted to do that is because assuming that the iodine and the NIR, what was that NIR model, these two numbers, they are the percentage of amylose content in rice. That's what I'm thinking. And so the only column that matches those numbers are these ycal and ytest. So I'm guessing that these are the training values um, for the amylose content values for uh, training, and these are the amylose content values for the test set. That's my understanding there. If you look at the y underscore test or y underscore cal, or not y underscore, it's just y cal dot shape. So we have just one column, and if we will try to get the histograms for this, so plt dot hist, I will try to get the histogram for the iodine and then overlay on top of those to see how similar they are or how different they are. So first one is iodine, and here we have alpha is equal to 0.9. So now when we run this one, let's put a plt dot show there. Okay, so that's how it lies between 0 to 35%. So that looks reasonable. Then the next one is we'll plot the NIR dash model. So NIR dash model, and now this one I'll set the alpha to 0.5, and it lies exactly on top of that. So the model predictions of the amylose do uh, coincide with what the actual readings were done by this iodine method. And the next one is plt.hist, and now we'll use the ycal. Alpha is equal to 0.5, and on here I'm going to add x label is amylose content, and that should be in percentage, and then plt dot y label, that's going to be just the count. And when we run this, now okay, so we do have a similar distribution. So I think that should be the right way to proceed, is to assume the ycal as amylose content and use that as the target variable. So this data set still does not have more than one target, but at least we have the issue of correlation that we can resolve with the least PLS method. Next, let's look at how the spectra look. So spectra, and for this we'll use a for loop to iterate through on the entire array and plot them. So first we'll try to plot just one. So plt dot plot, and here we'll use the values from the xcal, and for that we have x-axis, and for x-axis and then we have xcal for y, and we'll use the first row and all the columns from the first row and plot that. So let's add some labels. So plt dot x label, let me run this first. Now as you can see, these x-axis is not correct. The 4000 should be below this peak, and the 12,000 should be down here. So because these are the wave numbers where the actual magic happens, so these are 12,000 is towards 0. So what we need to do now is go back up here and flip the x-axis. So run that again, and now when we come back here and rerun this, we should get the flipped version of that. Okay, so we have this, and one trick that we can do to get it as it is in the paper, such that the 12,000 is on the left, we can invert that. So we can type plt.gca and gca.invert underscore x axis, and now if you type plt.show, so here we should be able to see it flipped. Okay, so now that's how you'll see it in the paper. So this is the area of interest, and these are mostly zero values down here. Not zero, but it's constant values. They don't change, and the peaks start right from here. So that's just one line, that one row that we have plotted. Let's go ahead and put a for loop and plot all of them and see how they look. Range, length, xcal. Now in a data set such as this one, if you need to confirm what each of those rows indicate or each of those arrays indicate, one way is to plot the data and see if the plots that you have match the plots that are there in the manuscript or the paper. If they match, then based on the discussion on that, then uh, you can find out what that array data in that array is indicating. Here this is wave number, and this is centimeter to power -1. Then the next one is plt.y label, and this is absorbance and abs, and then the one after that, I'll add the title is NIR spectra, and then yep, that should do it. So when we run this, we should see an overlay of all the plots. So in range, my mistake, so this should be in range. And after this is plotted here, as you can see now, we have all the plots listed. With that, we can also check our test spectra, how it looks. So this was, let's call this train, or this was for train, and we'll create a similar one for test. And here, instead of xcal, now we will use the x test. Again, same thing here, x test, and rest should, it could remain the same, and the plot should look similar. So as we can see, it goes from 12,000 to 4,000, and the y-axis from 0 to 1.75, and we have 12,000 to 4,000, y-axis 0 to 7, and the shapes also look similar, except as you'll notice that there is this variation here between different spectra, and that's what we'll address when we create the functions in part 2. So for now then, I think we have covered the visualization part. Let's take a small break and come back in part 2, where we'll do some function writing for pre-processing. Welcome back to section 2. In this section, we are going to write helper functions. So let's get started. Part 2, and the first one, the function that we'll write is to pre-process is MSC, which is multiplicative scatter correction. So for this, we'll create a function df the process underscore MSC, and what this does is it basically tries to mm, average out the graphs in a way. So for this, we'll zero mean each spectra from each row. So here we need to remember that the spectra is along the rows and not the columns. So when we do the zero mean, we need to use the axis 0. I'm going to transpose xt to np.mean x transpose and axis is equal to 0, and then return it to its original format by the outer transpose. And here we initialize temp is equal to an empty list, then initialize another c which is integer of length of what x has, and also create another x MSC. So this is the transformed version. So np.zeros x.shape, and now we can write the for loop here for the transform or process, either way. So for I in range x.shape 0, and then for j in range 0 c 10, then we have temp.append np.mean x from j to j plus 10, and axis is equal to 0. Then polyfit fit is equal to np.polyfit temp I, and then x I all the columns, and then 1 full is equal to true, and then update. So we update the MSC here, update that row with x I colon minus fit 0 and 1 divided by fit 0 0, and then we have return x underscore MSC. And so that's the first function. The next one is so before we create the next function, let's just see what is the effect of using this function on the spectra. How much does it clean it up? So x is equal to xcal.copy. So we'll create a copy so the original array stays intact as is. X underscore MSC is equal to preprocess underscore MSC of x, and then let's leave n is equal to length x underscore MSC, and for I in range n plt dot plot, and here we have x axis x underscore MSC I comma colon, and this is pre-processed one. So, and let me copy the same labels, paste them here, and let's run this. And with the plots, so as you can see here in this plot for xcal, we do not see, so previously we saw this width like a band of the spectra. Now it is more like a line, so the band has shrunken in the width. So that's one way we have tried to remove the noise from the signal, and that should help us in training the model. Now the next function we'll write is for scaling. That this is, you're probably already familiar with this using the standard scaler. Now the reason why I'm putting this in the function is because we'll use it several times and this makes it easy. X train, X test, Y train, Y test. So here I'm scaling both X and Y. So first we'll scale X, and for this, this small x, we have SCL is equal to pre-processing dot standard scalar, and here we have SCL dot fit x underscore train, and then we have transform. So x underscore train is equal to SCL dot transform x underscore train, and x underscore test is equal to SCL dot transform x underscore test, and then we have scale y. Scale y is going to be the same thing, except we are going to change the array names. So this is going to be y train, and this will be y train again. This is y test. We have y train and then y test. So with that, we can return the values. Return x underscore train, x underscore test, y underscore train, y underscore test. And here, just as a note, we could print a line that says that this function was executed and this is done. So we could say scaling was done. Scaling done. That should, and similar to this, we could add a line at the end of this function that says MSC done. So that's just like a pointer. Now with the scaling function done, the next one is taking the derivative. So this is another way, is taking the first and second derivative of the spectra. So for this, let's name this derivative. So the function name, I've set it to der, and this is only for the features, not the target. X underscore train, X underscore test, and dv is what order. So is it first or second? We can specify that here, and I'll save everything in a dictionary. So we'll initialize a dictionary here. So that's the initialize our dictionary, and that's the out. And then n names is equal to 0, and x underscore train. This is for creating the array names later on, before we send them out. So initialize names, and after that this is the for loop. So for x in x underscore train, x underscore test, c is equal to 0, and then for I in range length of x, we have d is equal to np dot gradient. So that's the first one, x, and this is for the each row. So we are working on row basis, not column basis here. And if the dv is set to 2, then we take the second derivative. So d is equal to np dot gradient, again of the same stuff, and then that's it. Now if c is equal to 0, then c plus equals 1, and if it's the first time, then we set the value of x underscore d to d, else we append. So x underscore d is equal to np dot, we stack, not append, but we stack it or concatenate it, x underscore d comma d. And once that is done, we can put that in the dictionary. So with the name equal to the name that's in the list that we initialized above, is equal to x underscore d, and then we also increment n by 1. So next time we pick the second item from the list, and then we can print, or if we need to, or we can simply say x train is equal to out x underscore train. So that's the key for the array in the dictionary. And then similarly x test is equal to out x underscore test, and we have that. And so with this we can say that this function was executed. So derivative done, and we can return x underscore train, x underscore test, and so that function is done. And lastly we have the fit model function. So we'll do the fit and predict. So for this we have def fit this, and x underscore train, x underscore test, y underscore train, y underscore test, and here we have PLSCR is equal to PLS regression, and n underscore components is equal to so here the number of components we can specify. So I'll set the default to 2, and then we use that here. PLSCR dot fit x underscore train, y underscore train, and then predict. So y underscore pred is equal to PLSCR dot predict, and this is x underscore test, and MSC is equal to matrix dot mean underscore squared underscore error, and then y underscore test, y underscore pred r2 is equal to matrix dot r2 underscore score, y underscore test, y underscore pred, and then we can return MSC and R2. Now what would happen is if we run this particular function through a loop to find optimal number of components that gives us the lowest MSC, then it could run into an error and crash. So that's why I'm going to add a try exception here. So you try this, and if there is an error, so accept and just pass, so it won't crash and continue that run. So that's the last function we have. So let's take a break here and come back in part 3 where we'll do the predictions. Welcome back in part 3. So far in part 1 we read the file, looked at how the data looks like. In part 2 we created all the functions. Now in part 3 we'll do the predictions and see how it looks. So the first item that I'm gonna do here is create copies. So x underscore train is equal to xcal. I'm renaming this and creating a copy. So we leave the original arrays intact. Y underscore train is equal to ycal dot copy. Now it is possible that xcal and ycal have a different purpose altogether than what I'm thinking about. But for this exercise, we'll think of them as x train and y train. So cal could stand for calibration, so maybe there's different step involved in there. So x test, y test. Okay. So with this, the next step is to zero out low values. So the reason why, let's leave this as is, and I'll come back to this later on. So I'll put the heading and write the code for this later on. The low values. Next is MSC, and for MSC X train is equal to preprocess MSC X underscore train. So all the curves would get updated here, and then similarly we process the test set preprocess underscore MSC X underscore test, and then we can have the derivative. So what we'll do is I'll put the code here, but then we'll use a select and see if what combinations of these give us the better predictions. So this is derivative and x underscore train, x underscore test. This is the first derivative, and then we have the scale. So all these could be put in a pipeline as well. Here I'm just typing them out as separate lines of codes. Y underscore train, y underscore test is equal to scale this, and this is again going to be the same stuff from the left hand side. So why not copy, paste it there. And after this we have the fit. So let's write that fit, and this is for fit. We'll run the fit through a for loop, and so for that I'm going to, the reason for running through for loop is because we do not know what number or which number of components would give us a better result. So this is max R2. I'm setting this value, best NC, so that's the number of components, and the MAC associated with that. And so for NC in range, we could also iterate it over a condition to get the lowest possible MAC and then use those components. So that could also be done. Range 2 to 100. The minimum 2 components, and we'll stop at 100 because pretty sure it will be somewhere in before that. The next, again I'll use the try catch, try exception here. So if the number of components used does not work, then it won't crash. R2 is equal to fit this, and we can specify the same extend itrain, and then we have nc is equal to nc. So that's coming from the for loop, and then here we can put a if statement. If R2 is greater than max R2, uh, which right now is set at 0, then update the values for these. So max R2 is equal to R2, then we have best NC becomes NC, then the underscore MAC becomes MAC, and finally we can print all the results from the for loop. So print NC, so these are the number of components, so why not write this n components, and this is NC. So best NC we are writing, and then we have print MSc, and this is MSc in print R2. So there is a so there is a debate as to w- you if you should be using R2 as the uh, value to check how good of a model you have, and it's not that reliable. And so but we still have it here uh, to use it as a reference, which we do have the MSc in there. Now that we have all of this written, this mistake here, so we need to fit double T. I think that's what we have. Yes, so that's what we have. Okay, so when we run this, we should be able to see the output. And okay, so 6 components, we have 0.62 as the MSc, and so that's the best we have is 0.62 right there. Now what we are going to do is do some changes here, but before we do that, there's one more thing I wanted to show is let's type PLSCR is equal to PLS regression, and here I wanted to show how the YPRED and uh, y test compare. Components is equal to best NC, that's from what we got above, PLSCR dot fit x underscore train y underscore train, and then we have y underscore pred is equal to PLSCR dot predict x underscore test, and MSc is equal to matrix dot mean underscore squared underscore error y underscore test y underscore pred, and here we'll do plt dot scatter y underscore pred y underscore let's do y underscore test and y underscore pred. Let's print MSc, we have it. Now when we run this, we see that that's the plot we have. So plt dot x label is y underscore test, and then plt dot y label is y underscore red, and we do plt dot show. And so with this here we can see that there seems to be some correlation between, so y test, if we assume if we assume that there is a linear relationship between the y test and y pred, then we would expect a straight line, the dots arranged along a straight line. However, that's not the case, but still we see that they are fairly close, which tells us that even though the predictions are not accurate, there still is potential that they could be improved upon. Now if we compare this with linear regression, let's see what we get. So here we'll try linear regression, and for this we'll use reg is equal to fit linear underscore model dot linear regression, and here we have reg dot fit x underscore train y underscore train. We have y underscore pred is equal to reg dot predict, and this is x underscore test. And now if we print, let's also get the MSc. So So MSE is equal to matrix dot mean squared error, and we have y underscore test, y underscore pred, and then we have R2 is equal to matrix dot um, R2 underscore score, again y underscore test, y underscore pred, and now we can print all of those. So MSC is MSC, and then similarly print R2, and here we can have the value of R2 and also get the plot. So plt dot scatter y underscore test y underscore pred. So why don't we copy this, the same lines of code? Okay, so now linear model is not defined. Let's import it from Scikit-learn, import linear underscore model. Okay, so as you can see, the difference, the biggest difference is, look at the MSE we have with linear regression. It's e to the power plus 20. So that's a massive MSE as compared to what we got uh, with the least partial least square. We have 0.62 as the MSE. So that's telling us that linear regression is not able to handle so many collinear features or correlated features in the X array that we have. So let can we do anything to improve this? Yes, we can. So what we are going to do now is, if we scroll back up and look at our raw data for the for this particular strain, let's copy this and look at one curve. I'm going to put that one right here, and let's look at just one plot. So as you can see, this particular part all the way up to maybe 9,000. So this is straight and constant. So what I'm thinking is, if we remove that part and see if that updates, if that helps us improve our lower our MSC further. So to do that, I'm going to add a few lines of code right here. So here we can cut this at, let's say, 0.22, and that will be somewhere right just above that horizontal line. Uh, and with that, we can have X train, and here X underscore train, and if the values are less than or equal to cut that we have above, then set those equal to 0. Same thing for X test, we have X underscore test, and similar way, if the values are lower than that, then let's go ahead and set them to 0 as well. And with this, let's see if what results we get. So let's run, and if the values improve, that's great. So the previous value was 0.6, so it didn't improve a lot, but we do see some improvement in the value for r square. It's now 0.78. So let me copy this and put it here, and we'll mark that cell as a RBC. Okay, so with that, now the next point we can do is try to see if removing any of these pre-processing steps help. If I remove, if we change the derivative to 2 instead of 1, then run this, then if we get improvement in MSC, great. If not, then we'll revert back to what we had, or maybe we could even try removing that. So the MSC increased to 0.8, So we definitely don't see any improvement with that. One thing I can try is completely eliminating the effect of derivative. So we had MSC plus derivative plus scaling. So I'm going to remove the derivative now and rerun this and see what we get. So far we had MSC, lowest MSC of 0.67. We can get any lower than that. That would be nice. Okay, so this is much better than 0.67. So let's copy this and put this here. So this was without, so here we didn't no derivative. We did not use derivative, no derivative. Now um, here another point that we could try is you could also try changing the value of cut. So if you go down is to 0.1 and see if that helps, or if you could go up. But you want to make sure if you are trying to go up, you don't want to cut off any of the peaks, because those are that bring information. So if you go down, the MSC increases drastically 5.4, so that's no good. And if you go up to 3, then 3 is not advisable, because 3 is you are right here, so you are eliminating this peak from the spectra, so you don't want to do that. But still we can look at the result and see if that changes anything. So here, this is very good result. We can see that the MSC has increased substantially, and that we don't want. And here erroneously one would think that the R square is 0.8, so this is a good step, but that's not actually good step, because the MSC is much higher, so you want to rely on the MSC. So let's put this back to what it was, which is 0.22. And now another question is, do we want to perform the MSC correction before we do any thresholding? Or so if we do that, let's try that. If we go back up here, put this here. So we are performing the MSC correction first, and then we can try to uh, do the thresholding. But then when we do the thresholding here, the thresholds are going to be different, because if we try to threshold at 0.2, we'll be removing a lot of data. So the thresholding would have to be somewhere at around, so this would be minus 0.5, and this would be minus 0.25, so somewhere around that. Let's try this. So minus 0.22 or 20, and let's run this. So this is another way we are trying to so here, as you can see, it didn't help. We have the MSC that's jumped to 9.7, and R square is also gone much down. So let's see if we can go further up to minus 0.25 and run this. And you'll see that I'm doing a lot of trial or error. So that's one way to see what combinations works. You could also do a cross validation on this and find the best components. So here we are at 0.297 as the MSC. So let me go back, and if you run this part, you'll see that they start to align. And if you run this model, again here the MS is just out of control, it's too high, and That tells us that linear regression is just not going to work for this type of data. Now, if I cut that and put it where this was, and again put this back to point to maybe 0.25, run this again, and this time I'm going to remove the scaling as well. Run this, and so we did. So here we have MSC that is now much larger. So removing the scaling did not help. So we definitely have to have the scaling in there. So that's how I would try and find what combinations. And in the paper, if you want to dig deeper, there are other ways in which they analyze the data, find new features, and adding those features could further improve the accuracy of the models. So if we want to compare this with we cannot compare this with the iodine Excel file we have, because we don't know which spectra each of those records belong to, unless they match the spectra array. So let's see what number of records it has. Spectra has 372 records, and the Excel file, it has how many? Let's print the size. Print iodine dot shape. There's 313. So now it's not the same. Okay, so in this video, then this is where we'll stop. We have the best MSE that we were able to get in this case was 0.39, and the R square was around 0.85. But we want to be careful how to interpret R square, because it does not necessarily suggest the how good a model fits. The next item we looked at was the MSE from the linear regression, and we see, okay, so with this combination that we have, MSE did drop down to 0.4, so it is now in a range which is comparable with the MSE uh, from the partial least squares that we have. So that's 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 there. That was it then for this video. I hope in this video you learned how to apply partial least square method such as PLS regression to a real world data set in Chemometrics. So this was to assess the amylose content in different varieties of rice from near infrared spectroscopy dataset. I encourage you to maybe read the paper or try out different combinations or other methods such as PLS canonical or CCA on the same dataset. Uh, or if you have access to MATLAB, you could try and see how other features were developed from this dataset and add those in the model and see if that improves, lowers the MSE of this particular predictions. If you have any comments or suggestions, please let me know in the comment section below. That helps me improve the video quality, and also it tells me that uh, the content is in line with what you're expecting. Uh, Please like, share, and subscribe. It helps me stay motivated to create more content for you all. If you have any other suggestions, please also feel free to post them in the discussion section of the channel. I hope to see you all in the next video on a new topic. Until then, thank you.